Hi, hello everyone. Welcome back. First and foremost, I'd like to introduce myself. I'm Mr. Reveles. Okay, I'm the AP Chemistry teacher and Pre-AP Chemistry teacher here at Canotillo High School, and I will be next door for any of your needs. If you guys are still having difficulties understanding these concepts after you watch this video, please feel free to come on, stop by my room, G211. You can also stop by Ms. Rosa's room, G215, next to mine, and also Mr. Villanueva's room, G216, around the hall, okay? If that doesn't work for you, you can also attend our tutoring sessions. Mr. Villanueva has a homework lab every day from Monday through Thursday from 4 to 5, and I also have tutoring sessions in my room, G211, from 4 to 5. Please attend if you need help. We understand what you're going through. Please don't be afraid to ask questions. We're going to try to do this format as best as we can. So at any time, if you need help, if you can't go to our tutoring sessions, reach us through Edmodo, okay? All right, so we're going to go ahead and get started with periodic trends. The other name is called periodicity, and we're going to try to do the best that we can in the small amount of time we have this week to teach you, okay? I'm going to go ahead and begin by introducing electronegativity, okay? So the electronegativity trend focuses on how well an atom can attract electrons to itself. Now, you have learned about valence electrons and their trend in the periodic table. You know that starting with the alkali metals, you have a +1 valence electron, which means that it's going to give away one. It goes to +2. Transition metals vary. And then we go to the boron group, the carbon group, nitrogen group, fluorine, and then finally noble gases. Fluorine, nitrogen, and oxygen, okay, I forgot about the oxygen group, they each have a very distinct quality, is that they stop being plus in their valence electron charge. They start being negative. A cation is a positively charged ion, meaning that it wants to give its electrons away to another atom. An anion is nitrogen, oxygen, and fluorine. They need this many valence electrons to fill their octet. So what does it mean in terms of their charge? What does it mean, mister? Well, let me explain. When it's positive, that atom wants to give away its electrons to another atom, okay, that's more electronegative. Now, why does it want to do that? Because everything requires energy. Just like you are not going to waste the time. If you have a remote control in your hand to go turn on the TV, you're not going to get up and touch the TV, right? You're going to use your remote. Whatever uses the least amount of energy is what will be accomplished, okay? For nitrogen, oxygen, and fluorine, they need 3, they need 2, they need 1. It is easier for them to accept electrons than to go searching for them. Because they are so close to filling an octet, meaning 8 valence electrons in total, they are not going to be as active in trying, they are going to be very active in trying to get those electrons, not as active as, the transition metals, but nonetheless, they're going to be active, okay? So electronegativity explains that trend. Now, a trend is a pattern that we see. In the periodic table, the trend goes like this. Electronegativity increases from the smallest period, from the largest period to the smallest, so from period 7 to period 1. And from column 1 to column 17, okay? So, fluorine is the most electronegative because it only needs 1 valence electron. But doesn't chlorine also need 1 valence electron? And bromine and iodine? Well, what makes these things different? Why is fluorine more electronegative than all of its other atoms in its family? Okay? It is because fluorine is the smallest in molar mass, okay? By being smaller, you also have less orbitals around your nucleus, okay? Fluorine exists in the second period, which means that it exists in the second orbital, okay? It exists in the p sublevel, which I know Mr. Marshall covered with you guys, and therefore, it is very active in trying to obtain electrons to bind to it, okay? Very active. Now, chlorine is also active. Don't get me wrong. The problem is chlorine's a little heavier, okay? Chlorine weighs about 35 grams per every mole or every atom, okay? So being that heavy, does not allow it to be as active. Just like us, right? I'm a pretty heavy guy. So I'm not going to be as active as, say, Anissa Burciaga track star, or, Marlon Jones, or, the guy from Jamaica, Usain Bolt, They're going to be way faster, they're way skinnier. I'm not going to be as fast. Is that clear? So this is kind of what we're trying to talk about. So electronegativity is how electronegative can you be? How can you attract electrons to you? And obviously fluorine is the smallest in that group, with needing only one valence electron, that is going to achieve that goal faster than anybody else. Now, why is this group kind of shaded out? Well, this is the noble gases, okay? And the noble gases are not electronegative in any way. The reason is because they have a full octet. They are stable, okay? By being stable, they no longer require the need to have to look for electrons to bind to its outer orbitals. They exist perfectly happy being who they are. They do not need any more influence. Okay, that brings us to our next point. Ionization energy. Okay? In electronegativity, we were looking at which atom can gain the electrons the fastest, right? Because it attracts it to itself very, very easily. The heavier the element, the least electronegative it is. And the lower on the periodic table, the lower the electronegativity rating is. Now, in ionization energy, okay, when we're talking about first ionization energies, meaning the energy it takes to remove the outermost electrons in the last orbital of these atoms. If you recall, in chemistry, we have periods. 1, 2, 3, 4, 5, 6, and 7. These periods represent the orbitals in those rows. Is that clear? In period 1, there's only one orbital. Hydrogen and helium exist on this orbital. Now, in your nucleus of the atom, the closer you are to the positively charged nucleus, the more the electron is going to be attracted to that nucleus. Okay? So, it's going to be harder for us to remove that electron if it's so tightly attracted to the nucleus. Now, as you increase orbitals, you increase the separation from the nucleus. Okay? The further apart you are from the nucleus, the easier it is to take away an electron from you. Okay? So, let's look at it in terms of the periodic table. Francium is one of the heaviest elements in the periodic table. It's not the heaviest, but it's one of the heaviest. Has theoretically 7 orbitals around its nucleus. Okay, 7. Now, if you can think of hydrogen, hydrogen's nucleus and its proximity to its next electron is about you standing and there being 3 football fields away from you. So imagine standing outside the football field at the end zone and adding 2 more football fields. That's how close an electron is to its nucleus in real life. Okay? So, imagine 7 orbitals. How far are those electrons from the nucleus? So the first ionization energy is in relation to the outermost orbital. Okay? How much energy do we need to take it away? When they're this far, you don't need a lot of energy to take away those electrons. When you're this close, you need a lot of energy. When you're helium, I'm going to use these markers as electrons, okay? I'm the nucleus of helium, and I have a full octet. I have 2 electrons in my first orbital. Now think, is it going to be easy for you guys to take away these electrons from me? The answer is no. It's not going to be very easy. You're going to require a lot of energy. Now, if I were to be francium, okay, what francium is it gets bigger, right? Holds more electrons. This is how I would do an analogy. I'm holding way more electrons than I need. Okay? Okay. Is it going to be easier for you to take these electrons away from me? I'm going to hold on to them tight, but is it going to be easier? Yes. Because I do not have the energy to sustain all of them. I'm heavier, right? I don't have enough hands. Another analogy is when you go to the store, right? Your mom tells you to bring down the groceries. If you only grab 2 bags, pelada, right? But now, you try to be those tough guys, right? That carry like 6 bags at a time. Now, think of taking away one of those grocery bags from a person. It's pretty easy because they're holding them maybe with their pinky or with 2 fingers. So the more grip we have around it, the harder it is for our first ionization energy. Okay? So we would require a lot of energy in smaller atoms. We would require less energy in larger atoms. Is that clear? All right. Well, thanks for watching. Please respond to Edmodo comments. Do the worksheet that's on Edmodo and read the notes. The notes on periodicity. Okay? Thanks for watching, guys. We'll see you next time.